So now I would like you to do some practice problems. If you've not had a chance to look at these practice problems, pause the video, go do them, and then try these with me going over it. I want you to try it first. If you've not tried it first, go do that, pause, come back. Now, assuming that you have done that, I'm going to resume. So it says a really big ball is dropped from the top of a 12-meter tall building. Draw an energy pie chart for each of the positions of the ball as it falls down. The ball has a mass of 5 kilograms and it is not moving at the top when it is first dropped. And the ball is so close to the ground at the bottom position that it is both moving and you can assume it is at a height of 0. So at the top, it said that it was not moving. So if it's not moving at the top, that means my kinetic energy is 0. So my velocity at the top is 0. And at the bottom, I had a height of 0, but it was still moving really fast. Well, that means that I'm going to have a big kinetic energy and no gravitational potential energy. So I'm going to fill that in, that I'm going to have big kinetic energy here. Now at the top, at 12 meters tall, I'm going to say, and I'm going to start filling in this table as well. So this table is really handy for keeping track of all your information of how much each of your energies are. So at the top, that is 12 meters up in the air. And I know that it's not moving, which means that I have all gravitational potential energy. And the closer I get to the ground, the less I'm going to have. So I'm going to have a little bit less here. And then I'm going to have a little bit less yet. And then the rest of this is going to be kinetic. Now I have all of my gravitational potential energies and kinetic energies shaded in. And you'll notice now that I have it shaded that it's really obvious that the closer I get to the ground, my kinetic energy gets bigger and bigger, and my gravitational potential energy gets smaller and smaller the closer I get to the ground. So at this point, I'm going to plug in what I know into this table. So I know that the top is at 12 meters high. I know the bottom is at 0 meters. And so when my thing is at the top, I also know that my velocity was 0. So that means that my kinetic energy was 0 at the top. I also know that there are no springs in this at all. So I know my spring potential energy is 0 for all of these. And at the bottom, I know that my height is so small, I'm saying it's 0, which means my gravitational potential energy will be 0 at the bottom. Now, what's kind of neat about this table is the way it's designed is using the concept of conservation of energy. So I know that the total amount of energy needs to be the same the whole time. So if I add my gravitational potential energy with my kinetic and my spring, I should get my total energy. And the same thing applies to each of these. So then the question is can I figure out some other stuff to fill into this table? And the answer is yes. And I'm going to do that as I go through this question because it'll kind of guide me through what to do. So the first question says, how much gravitational potential energy is there at the top when the ball is first dropped? So I'll notice that it says gravitational potential energy. So that's my GPE. And I'm going to look back at my notes and remember that that is equal to my mass times g times my height. And I'm not going to worry about doing units here, so you don't need to either. But my mass in this problem is 5 kilograms. And g, because we're on Earth, is 9.8. So whenever we're on Earth, g is 9.8. And then my height is 12 meters. So I just type that into my calculator and I get 588 joules because the unit for all of energy is joules. So I'm going to go ahead and plug that in right here into my GPE. So that's my gravitational potential energy of the ball at the top. Well, I'll notice now that these things, if I add them up together, I will get my total energy. And that's what the next question is asking, is what is the total energy of the ball? So in this row, I have everything I need. So I can go 588 plus 0 plus 0 is 588. And then we know, because of conservation of energy, that however much energy I have at the beginning needs to be the same as the energy at the end. So if it's 588, it's still going to be 588 the entire time. So once you know one, you can just fill it in for the rest. Now, the next thing I'm going to read is the next question, which says, at a certain point called the lower middle, there is 200 joules of kinetic energy. So I'm going to write this in. Here's my lower middle. There are 200 joules of kinetic energy. How much gravitational potential energy will there be at that moment? Well, I'm going to remember that if I add my types of energy together, this one plus that one, I need to get 588. Well, that means that I need 200 plus something is 588. So I'm going to subtract 288 from both sides. And what I get is a gravitational potential energy of 388. So I'm going to check it. 388 plus 200. Yes, that's equal to 588. And last but not least, so then I can fill this in. The total energy of the ball is 588 joules. And the lower middle, my kinetic energy is 200, and that's when my gravitational potential energy is 388. So the next couple are slightly trickier because now you're given an amount of energy and you need to solve for something else in the equation. So I recommend you write down the equation first, plug in what you know, and then solve for what you don't. So when there is 200 joules of kinetic energy, how fast will the ball be moving? So I'm looking for a velocity here. And so I'm going to start by writing the equation for kinetic energy. That kinetic energy is equal to 1/2 times mass times my velocity squared. And my kinetic energy here is 200 joules. And that's equal to 1/2 times my mass, which I'm going to remember is 5 kilograms, times my velocity squared, which I don't know, so I'm going to just put it as velocity squared. So the first thing I can do is I'm going to multiply the 1.5 times the 5. And I'm going to not worry about my units here because that's just going to make things more confusing, so I'm going to get rid of those. So I have 200 is equal to 2.5 times v squared. Now, when I'm solving for something, I need to do the opposite. So because it's 2.5 times v squared, I need to do the opposite, which is division. So I'm going to divide both sides by 2.5. So 200 divided by 2.5 is 80. So 200 divided by 2.5 is 80. And that's equal to v squared. So again, I need to do the opposite. So if I have squared, then I'm going to do the opposite, which is square root. So I'll take the square root of both sides. And the square root of 80 is 8.9. And so that will be equal to my velocity. Part F is a little bit easier. So if you struggled with E, do not worry. F is a little bit easier. Now it says you found how much gravitational potential energy there will be when there is 200 joules of kinetic energy in part D. Find the height of the ball at that moment. So we're going to use the gravitational potential energy here to solve for my height. So my gravitational potential energy, or GPE, is equal to m times g times my height. And my gravitational potential energy is 388 joules. My mass is still 5. G, because we're on Earth, G is always going to be 9.8. So I'm going to put 9.8 times my height. And that's what I'm trying to find. So I'm just going to put H. And then all I need to do is I'm going to combine the 5 and the 9.8 together. So 5 times 9.8, which is 49. And then again, I'm going to do the opposite. So because it's 49 times H, I'm going to do the opposite of that, which is division. So I'm going to divide both sides by 49. That'll cancel out on this side. And I'll be left with 388 divided by 49 is 7.9 meters is going to be my height. So that's number 1.